Everyone, this is Shatrupa and I'm going to present our paper Binary Select to improve accessibility of black box attack. We are going to look through few things like what is the motivation of the paper, the experiments that we ran, methodologies, the data set that we have used, and certain results, graphs, and definitely the future work. So, adversarial text attacks have become a key focus in NLP research that is crucial for assessing models' robustness and addressing privacy concerns. These attacks involve crafting inputs to deceive the machine learning models, causing misclassification or incorrect output. Black box attack with limited model knowledge pose challenges needing numerous queries to identify influential word or tokens. This iterative process, especially with longer text, consumes substantial time and resources, hindering effective research. We propose binary select, integrating binary search with adversarial strategies, offering efficiency over greedy select. Unlike greedy select, binary select systematically partitions into two segments, reducing the query significantly while maintaining the effectiveness. So there are certain classifiers and data sets that we have used. We have used 5 classifiers. Those are Albert, Robota, BERT, Distilbert, and LSTM. And the data set that we have worked on is IMDb, AG News, and Yelp. Majorly, the basic and the initial experiments were started using the IMDb data set. Moving on to the methodology, we get to talk about the two method where we compare greedy select with binary select. So in the visualization, you can see that greedy select selects one word at a time and checks its probability, while binary select continuously splits the text into two halves and excludes the segment which has higher drop. And then further, it divides the segment with higher drop and again it keeps splitting, so on and so forth, and eventually the splitting leaves us with only one word which is chosen. Greedy select is a technique in black box attack for finding mistakes or misclassification in text classifier. It removes one word at a time from a text and identifies the word causing the most significant drop in the target class probability. This approach, requiring n queries to the classifier, is effective for evaluating the classifier robustness in NLP tasks. In the context of greedy select, we use the variable f to represent the classifier, being f represents the classification score, which is essentially the probability assigned to a certain class by the classifier. When the greedy select evaluates each word in the text, it systematically removes the word and calculates the score using the formula that is written below. The purpose of this calculation is to determine the impact of removing each word on the probability of the target class. Greedy select then chooses the word that results in the most significant reduction in the probability of the target class. This selection process is crucial as it helps in identifying the word whose absence has the most substantial impact on the classifier's classification score. Ultimately, this aids in understanding which words are crucial for classifier's decision-making process, providing insight into the key factors influencing the classification outcomes. Binary select, on the other hand, uses binary search to find the most impactful word in the text of length n. It divides the search space into two halves, requiring 2 times log n queries to isolate the keyword. This efficient strategy reduces search complexity and is effective in adversarial attack scenarios. The algorithm continuously splits the text until a single word segment is found, selecting the segment with the highest probability drop to identify the critical word. In binary select, the classifier is represented as F and the classification score is denoted by the text. X is denoted as f of x. When binary select partitions the text into two segments, that is x1 and x2, it calculates the probability of f of x1 and f of x2 by excluding these segments from the original text. This exclusion is based on the principle that removing certain segments can influence the classifier's classification score. The algorithm then computes the difference in probability and finds the score for each segment. The change of probability of certain target class when the segment x of 1 or x of 2 is removed from the original text. By analyzing these changes, binary select identifies the text with the highest probability drop, indicating its significance in influencing the classifier's classification score. Furthermore, binary select may iterate this process until a single word segment is achieved, allowing for the identification of the most influential word or segment. This iterative approach helps in pinpointing the word or segment that has the most significant impact on the classifier's classification score, providing valuable insight into the factors deriving classification outcomes. Initial experiment that we ran on binary select versus greedy select was a simple experiment where we compared the binary select and greedy select in finding the most influential word, where we used fine-tuned Albert classifier on 1000 data set of IMDb. Results show that binary select's logarithmic query count trend versus the greedy select's linear trend, indicating binary select's computational efficiency especially for longer text. This makes binary select more suitable for practical application, maintaining stable query count regardless of the input size. Of the attack. Our study explored binary select's effectiveness in adversarial attack within a comprehensive framework comprising word selection and replacement stages. Binary select aids in pinpointing the critical word position crucial for the classifier's decision making, ensuring a systematic approach. For the word replacement, we adopt a strategy similar to the PWWS, the probabilistic word weight scheme, querying WordNet for synonyms and choosing replacement, leading to the classifier failure or significant probability drop. This iterative process enhances the adversarial example creation while maintaining the semantic coherence. Is binary tree structure used, or why is it even important for this paper or research work? While implementing binary select, we faced a challenge in memory management due to its iterative text splitting approach. To address this, we used a binary tree structure to track previously scored segments, minimizing the need for additional queries and optimizing efficiency. The tree structure is updated as new segments are evaluated, allowing binary select to effectively manage memory, and streamline operations, and reduce queries per attack iteration. This example demonstrates sentiment analysis using sentiment scoring system where negative sentiments are assigned lower scores. Each sentence or phrase is assigned a sentiment score, with higher negative sentiments receiving lower scores. In this case, the phrase, "This movie is definitely the worst I have ever seen," is given a sentiment score of minus zero point 0.9, indicating strong negativity. As the sentence becomes less negative or shifts in context, the score increases accordingly. For instance, "The movie is definitely this part has minus zero point 0.7, and "worst I have seen" has a score of minus zero point 0.4, which indicates a slight less negative sentiment with score of minus 7, score of minus zero point 0.7, which increases to a score of minus zero point 0.4 as the sentiment improves further, with "worst I have ever seen" being minus of zero point 0.6. The sentiment scoring process is illustrated using binary tree structure where each node represents a phase or a subphrase, and the branches represent the sentiment score. This tree structure helps visualize how sentiment analysis assigns score based on the context and composition of the text. used to restrict the values of k. To improve the efficiency of our attack strategy, we introduce k values that limits the maximum modification to k words within the text. Increasing the k value can enhance the attack's effectiveness but also lead to a higher number of required queries. The parameter k provided with a tool to balance the attack's effectiveness and efficiency, especially for those with limited resources. Different dataset may benefit from varying k values, and our investigation tested k values for 5, 15, 30, 50, and for all, where all indicates no restriction on word replacement. Higher k value results in increased query numbers and reduced accuracy of the targeted classifier. At k equal to 5, minimal queries are required and target model accuracy remains strong. However, at k equal to all, accuracy experiences a significant drop accompanied by an extensive number of queries. The optimal k value aims to strike a balance between the minimizing accuracy loss and reducing the query count. In our case, k equal to 15 achieves this balance. Although k equal to 30 may offer a similar equilibrium, these findings stress the importance of evaluating various k values for effectively meeting different trade-off objectives. The use of k values help us navigate the trade off between the attack's effectiveness and efficiency, ensuring that our attack strategy remained both impactful and resource efficient. The parameter k serves as a valuable tool for balancing these trade offs, particularly for researchers with limited resources. Main result of our attack experiments can be found in this table. For each classifier, we compare the greedy and binary select. We use a k value of 15, which means the attack was limited to replacing 15 words in a text at most. The first three matrices described are original accuracy, attack accuracy, average query, and average query success. Binary select reduces the number of queries greatly with some drop in the attack effectiveness. We see drop in query amount for both IMDb and Yelp dataset. Focusing on the Albert classifier, we see a 31% difference in query between greedy select and binary select. This drop in query caused a slight drop in attack effectiveness of 16%. Similarly, for IMDb, we see a larger difference in queries. Specifically, binary select causes a 46% reduction in queries compared to greedy, with a 23% drop in attack effectiveness. We focus on the number of queries for successful attack when this increases to a 54% reduction in queries for the same 23% effectiveness trade off. Hence, we see a stronger positive effect in query reduction compared to the attack effectiveness. Graphical comparison between all the k values of different data sets, as you can see for AG News, IMDb, and for Real. We verify the main result of binary select by extending the experiment to character level attacks. Specifically, we target a character level model fine tuned on SST2. Stanford's sentiment tree bank contains movie reviews labeled for sentiment dataset. We leverage binary select and greedy select to choose which character to modify and use the ECES Unicode replacement from Viper. To replace each chosen character, we run the attack for k equal to 5 and k equal to all on the validation set. The result can be found in this following table that you see right here. We observe the results consistent with the word level attacks. For lower k, we see binary select outperform greedy select, while for larger k, we see similar attack effectiveness and similar query counts. However, again, for the successful cases, binary select strongly outperforms greedy select, which further points to the potential strength of binary select. We see that binary select better performs with fewer word changes while greedy select is more efficient for larger modification. Combined binary select and greedy select using an oracle model on IMDb dataset for distal birth, we see the result on the table highlighted next to the writing. The oracle reduced queries by leveraging the binary select for smaller changes and greedy select for the larger ones. The challenges that remain in developing a practical automatic oracle for determining the required number of changes. In conclusion, binary select has shown promising in enhancing attack efficiency by significantly reducing query count while maintaining effectiveness. Its integration with WordNet replacement techniques and parameters like K control enhances the versatility and adaptability across domains, offering a flexible approach. Binary Select's streamlined process and feature makes it a cornerstone in advancing adversarial attack strategies, promising practical application in the real world scenarios. Work definitely holds integrating word embeddings, enhancing the attack by using word embeddings in the replacement stage. Word embeddings offer different context aware word representation. They generate more relevant suggestion for replacement. Second, being the human validation method, we integrate human validation method into the attack process is crucial. Binary select and greedy select depend on classifier feedback, but human validation would add more insight. Human feedback will enhance understanding the word replacement in semantic contextual context. Lastly, optimization of k value will act as a prime thing, which sets the maximum word replaced in an attack is vital for balancing attack effectiveness and efficiency. Future work can systematically experiment to find the best k values for various dataset and classifiers. By optimizing the k value, researchers can strike a better balance between the attack success and the query count, enhancing efficiency in adversarial attacks. Thank you.